Hello and welcome to another lecture of classical motion of a single particle. So, already we have discussed different concepts regarding conservative force fields, how a conservative force field can be expressed as a gradient of a scalar function which we call potential. We also said an interesting property related to that is that for a conservative force field, the work done which is not necessarily a state function reduces to a state function, and actually if you know the potential function, then you can easily calculate the work done for a conservative force field. In short, you can also say that the work done is independent of path for a conservative force field, which is not in general true if your force field is non-conservative. So, although we have discussed various theories and some general formulations, I thought it would be somehow helpful for the students to discuss the topic with a concrete problem, and that is why before going to the discussion on central forces, I would like to spend this lecture for a little bit solving a typical problem where we are supposed to calculate the work done under different type of force fields. Okay. So, before that I will be just trying to tell you one thing, that work done we have already defined. So, we said that work done is nothing but integration over f dot dr, and where dr is the infinitesimal displacement and the force is the f is the force acting on the particle. And we also said that this is not in general a state function, and that is why this is when this when you do d of w, this is not an exact differential in general. Okay. And but we also said that if your force is written as minus of some gradient phi, once again minus is just a conventional thing, it can be plus as well, and then your total w will be integration over minus gradient of phi dot dr, which is equal to minus of d phi integration, and then you know this is nothing but minus of phi final initial. So, it is nothing but phi initial minus phi final. Okay. So, that is what it is. Now, this type of integration is very easy when we give you the force field as a function of the space coordinates, because if you know f as a function of x, y, z, then of course you know that dr will be simply dx I cap plus dy j cap plus dz k cap, and you can just by knowing the initial point initial space coordinates and the final space coordinates, somehow in principle you should calculate this work done by like this. Okay. So, if I just write this one is the work done, then I should be able to calculate this. Okay. Sum from x I, y I, z I to x f, y f, z f. Okay. So, that we have to know. But now the point is, if your so I should make this dot product clear, okay, so that there is no confusion. Yeah. And now instead of that, if we are giving you a force field which is an explicit function of time, so you exactly know the force field as a function of time. Okay. So, this how to then calculate the force, okay, how to then calculate the work done. Okay. So, of course, for that you have to also know the dr in terms of t. Okay. So, what is the way out, and for that then we have to actually have to do the simple thing which is the main objective of classical mechanics, that is to solve the Newton's law. So, if you really understand the Newton's law, this is m dv dt is equal to f. Now, if you remember some in some of the previous lectures, or rather in one of the previous lectures, I said that if f is a function of t, then this is quite easy to get v for constant m, v will be simply given by this f t dt. Okay. and here we exactly will use this fact. So, if we have f, then actually our mv will be is equal to this integration 24 t square I cap plus 36 t minus 16 j cap minus 12 t k cap dt. Okay. Now, you see at this point we have to make two comments. One is we have to now give some value to the m, so that we can use this as a constant of the motion. So, m is, I just for the sake of simplicity I assume this to be 1. So, I can forget this, then my v will simply be equal to, if you integrate this, v will be. So, now you see this is a vector integration. So, it has 3 parts, okay, but 3 parts are independent. So, I just write this unit vector for this part. So, I cap, it will be multiplied with simply integration 24 t square dt plus j cap 36 t minus 16 dt, and finally minus k cap, you will have 12 t dt. Okay. So, integration of course. So, if you do correctly the calculations, you will see here you will have 24 times t cube by 3. So, it will give you finally 8 t cube I cap plus this first term will give you 36 times t square by 2. So, which will be 18 t square. So, j cap times 18 t square minus 16 t. So, I can write that 16 t. Okay. Finally, this part I can write 12 t square by 2, which is nothing but minus 6 t square k cap. Okay. So, this is not the end. We have to add an arbitrary constant of integration, and that is, I can call that a k 0. This is a constant vector. So, when we integrate scalars, we have a constant number or constant scalar. Here we are integrating a vector, and that is why we will have a constant vector as a arbitrary constant of integration. Okay. So, how to calculate this one? For that we now need the access to initial conditions. So, what would be v and the position r at some given instant t is equal to some t 0. So, here for this problem what we have chosen is this one. We have said the initial conditions at t is equal to 0, the particle is at r 0, which is equal to 3I minus j plus 4k, and it has a velocity v 0 at t is equal to 0 of course, which is equal to 6 I cap plus 15 j cap minus 8 k cap. Okay. So, now I already know v is equal to 8 t cube I cap plus 18 t square minus 16 t j cap minus 60 square k cap plus k 0 vector. Okay. At t is equal to 0, all these terms would vanish and v will be equal to v 0. So, from that we easily can say that v 0 is equal to k 0, and that is equal to the given vector 6I plus 15j minus 8k. So, if you use that, so your actual v will be, instantaneous v will be this value plus the value of v 0 or the k 0, which are equal, now we have just shown. So, it will be actually, if you write completely, 8 t cube plus 6 I cap plus 18 t square minus 16 t plus 15 j cap minus 6 t square plus 8 k cap. So, this is the specific solution for v, the velocity. Now, if I know that, I can go to one step further, I can simply write this is equal to dr dt. Okay. And if this is equal to dr dt, actually I can again use the same formula that dr dt is a function of t. So, r can be simply obtained by just doing a time integration over the right hand side. Okay. So, I just write this once again. So, this is equal to the whole expression here. So, instead of writing the final, writing the step by step all the calculations, I will simply directly write the r vector here, which can be written as 2 t to the 4 plus 6 t I cap plus 6 t cube minus 8 t square plus 15 t j cap minus 2 t cube plus 8 t k cap plus another constant of integration, okay, which I denote by k 0 prime. Now, again at t is equal to 0, all these terms do vanish, and that is why finally you have. So, initial conditions imply r 0 will be exactly equal to k 0 prime and will be equal to 3 I cap minus j cap plus 4 k cap. Okay. If you use that, then finally for the final expression of r, you will get r is equal to, I can use a different color or the original color which I was using, r is equal to 2 t to the 4 plus 6 t plus 3 I cap plus 6 t cube minus 8 t square plus 15 t minus 1 j cap plus 4 minus 2 t cube minus 8 t k cap. Okay. You see, this is the final expression for the displacement vector. Now, once I know displacement vector, I can immediately write the dr vector. Dr vector is nothing but, so this is just a function, r is a function of t. So, if you do dr, the finally the infinitesimal will be transferred to t. Okay. So, it will simply be, then you will have, then I would write, if you remember the expression of d is that expression of r is that this one. So, if you correctly do the calculations, dr would get 8 t cube plus 6 I. I request all of you to do that independently and cross check. 18 t square minus 16 t plus 15 j cap. Let me just check one thing. Yes, yeah, plus, oh, maybe this is minus sign over here, yeah. Then finally, it will be minus 6 t square plus 8 k cap dt. Okay. So, this is a vector now, infinitesimal vector, whose infinitesimal is actually now transferred on t. Okay. And then finally, I have dr and I know f as a function of t. I know now dr as a function of t, then I will do the integration. I will first do the scalar product. So, if you just do something like this, so this will be equal to 24 t square I cap plus, so that is the expression of the force, if you remember, 36 t minus 16 j cap minus 12 t k cap. Then you just take the dot product with this is this whole thing. I just write here just dr, so that you can easily write it. And so there is a dt. Now you integrate. So this will be an integration over t. Okay. Now if you do the integration over t, now I can tell you that okay, I would like to know the amount of work done to move a particle between the time instant t is equal to 1 to t is equal to 2. If I say that, then finally you can give me a value for that work done, which will be 1 to 2. Then if you do that calculation cautiously, you will have something like that: 24 t square 8 t cube plus 6 plus 36 t minus 16 18 t square minus 16 t plus 15 plus 12 t 6 t square plus 8, and everything is multiplied by dt, and t is varying from 1 to 2. Okay. So if you do this calculation, you will have this. So there are several ways to do the calculation, since there are big numbers like 36 times 18, 36 times 16, 16 times 15. So I have done something what I in general prefer. So I do not immediately multiply them for obtaining the value, but I just keep them as product. For example, here, and then I did the integrations. For example, this term. So this will give you 24 times 8 t square times t to the t cube, which is t to the 5 dt. If you integrate, so after being integrated, it will be giving you t to the 6 by 6. So this is t to the 5 dt, so which is nothing but t to the 6 by 6. So I use directly that, and what I what I obtained is the following: 24 into 8 t to the 6 by 6. I am just doing the calculations by one term, so that you can actually cross check carefully, okay, and thoroughly. So the second one is plus 24 times 6 t cube by 3, because you see here is a t square and there is nothing. So t square dt will be t cube by 3. Okay. Then you have other terms which I write successively, like 36 times 18, then t to the 4 by 4. Then you have minus 16 times 18 by 3, t cube by 3 will come. Then here will be another minus 36 times 16, again t cube by 3. Okay, 3 I just write like here, so that it will be easier to recognize the cancellation, plus 16 times 16 t square by 2 plus 36 times 15 t square by 2 minus 16 times 15 t plus 72 times t to the 4 by 4, and finally plus 96 times t square by 2. Okay. And everything is then evaluated within 2 and 1, because this is the upper and lower bound for t. Okay. You can do several cancellations, for example 6, 4, 3, 8, 4, 9, 3, 6, 3, 12, 2, 8, 2, 18, 4, 18, 48. Okay. So if you do everything and calculate very carefully, you should get the total answer to be equal to 4134 unit. So that is the work done by the system. Okay. And look, this is having a positive value. That means the work done is really by the system. Okay. So, according to our convention, whenever the work done is positive, the work is done by the system, and whenever the work done is negative, the work is done on the system. Okay. So, you see that that was a very simple problem, that we know f as a function of t, but to calculate the work done, what we actually had to use the equations of mechanics, equations of dynamics, the Newton's laws, and we are starting from f is equal to ma or m times acceleration, we integrated to get velocity and the displacement, and finally from this displacement we calculated the infinitesimal displacement and we calculated f dot dr integration. Okay. Now, if you just think that I also mentioned about the famous work energy theorem in one of the previous lectures, and there I mentioned that work energy theorem is a very general theorem where the work done is nothing but for a particle just moving under some force F, the work done is exactly equal to the change in kinetic energy. Now, if you do some calculation much easier than this one, you will actually find that you can, instead of calculating this work done like this, I mean using this long process, you can calculate this amount of work done just by using work energy theorem. How is that? For that, you have to actually calculate the kinetic energy of the particle at some time t is equal to 2 minus kinetic energy t is equal to 1. So, now if I just say how to calculate the kinetic energy, remember you have the total V vector. Okay. So, you can calculate the value of V vector at t is equal to 2 and also at t is equal to 1 just by substituting the values of t, okay, properly. Then you will, for every V vector you can calculate the corresponding modular squares, which will nothing but be the square of this part plus the square of this part plus the square of this part. Okay. If you do that, you will actually can check that the delta of kinetic energy will be exactly equal to again this amount 4134 unit, will be again 4134 unit. Okay. There should be a plus minus problem always, that depends on how you which difference you are taking. Okay. So, if kinetic energy is reduced, that means the work is done on the system and the work is actually stored in the system as potential energy. On the other hand, if the kinetic energy increases, that means the work is done by the system, which now loses some potential energy. Okay. So, this is the concept of work done. Now, in the second part of our discussion, we will be actually discussing a comparative way to distinguish the conservative force field and the non-conservative force field. And we will actually show that if you take a conservative force field and a non-conservative force field, really for the case of conservative force field, you will have the work done which is properly independent of the path chosen, but this will not be true for non-conservative force field. However, you should not forget the message that irrespective of the force field is conservative or non-conservative, you will always have work energy theorem to be true. So, for this second part, what I will prefer is that I will directly take, so I just give the name conservative versus non-conservative forces. Okay. This part I will do somehow briefly, so that I will tell you some hints and you can do some calculations at home. Okay. I take two force field F1, which is 3x square I cap plus 2xz minus y cap, minus y j cap, plus z k cap. F2 which is equal to 2xy plus z cube I cap plus x square j cap plus 3x z square k cap. I would like to calculate the work done under those two forces, and of course, you can say this time I have given you the force as a function of the space coordinate. So, you know dr is not a problem at all, this is dx I cap plus dy j cap plus dz k cap. But we can of course do this calculation of the work directly explicitly, but before that we can also check something which is much more interesting. So, whenever this type of problem of calculating work done you can encounter in tests, in interviews or wherever, the first task is to check the curls of the force field. So, this is of course, this is somehow it is not hard and fast rule, but it is always a trick and it is a very useful trick. So, if you do the curl of F1, you will see that this is I cap, j cap and k cap, and del del x, del del y and del del z. Okay. So, I just write 3x square, 2xz minus y and finally z. Okay. What will be the curl? So, for I will have for the ith component, the x component I will have, so 0 minus 2x plus j cap times del del z of 3x square is 0. So, del del x of z which is also 0 plus k cap. Now, you will have 2z minus 0. So, you will have actually minus 2x I cap plus 2z k cap. So, this is not a null vector. So, this force field is not conservative. So, is not conservative. What about the force field F2? Okay. So, F2 I am also calculating the curl now. So, that will be del del x, del del y and del del z. So, 2xy plus z cube x square and 3xz square, that is what is written over here. So, what will be the curl? I cap will be, so this will be 0, del del y of 3xz square will be 0, del del z of x square will also be 0 plus j cap. So, del del z of 2xy plus z cube will simply be 3z square, and then del del x of 3xz square will also be minus 3z square plus k cap. So, you now have to say del del ddx, del del x of x square which is 2x minus del del y of 2xy plus z cube which is also 2x. So, it will be 2x minus 2x, and finally, you have a null vector. So, this one is conservative. Now, if I give you an exercise that under these two forces you have to go to, so you have to, so calculate, I just write this, calculate the work done to move a particle of, let us say, mass unity or 1 from 0 0 0 to 2 1 3, this point to this point. So, x is equal to 0, y is equal to 0, z is equal to 0, 2, x is equal to 2, y is equal to 1 and z is equal to 3. Okay. So, that is the final point, that is the initial point. So, now we have to do the exercise along two different paths. One is the straight line joining those points, and the second one is along the space curve x is equal to 2t square comma y is equal to t comma z is equal to 4t square minus t. Before even calculating anything, we already have the information in at hand is this one is a curless field. If this one is a curless field, basically we can immediately calculate the f dr. So, f dot dr, and that will be, so I know, so that will be for example from this point like 0 0 0 to 2 1 3. Okay. So, if I do that, I can have, so I just write this zeros, I mean I can call that point I and this is as point f. So, instead of writing many, I mean like instead of writing this every time, I just write this from I to f, and then what I will say that this f is this one. So, 2 x y plus z cube I cap plus x squared j cap plus 3 x z square k cap. Okay. I just check that, yes, this is the correct expression, x square, yes. Okay. Now, I have this dx I cap plus dy j cap plus dz k cap. Okay. So, I can now write this is integration I f. Okay. You will see 2 x y plus z cube dx plus x squared dy plus 3 x z squared dz. That is when you contract these two vectors you obtain. Okay. And then you can simply say that 2 x y dx and x squared dy, they make actually d of x square y, and then z cube dx plus 3 x z square dz actually combining these two, they will give you d of x z cube. Okay. So, finally, you will have integration I to f x square y plus x z cube and d of that whole function. So, finally, what will be this? The final value of this function minus the initial value of this function, and what is the final value of this function when this is at the point 2, 1 and 3, and what is the initial value when everything is 0, 0, 0. So, this is value is 0. So, when x is 2 and y is 1 and z is like 3, then if you calculate, actually you will get, this is simply 2 square times 1 plus 2 times 27. So, this is 3 cube, and you will have 54, 58 units. Okay. So, that is the work done. Now, the point is, the interesting point is, if you now go to any, go along any path connecting these 2 points, the work done will always be equal to 58 units. So, what I will do here, I will simply do the path which is nothing but a straight line. So, I just take the straight line. So, calculating the work done along the straight line joining 0 0 0 and 2 1 3. Okay. Now, if you do that, So, what will be the equation of the straight line? You know that will be simply x by 2 is equal to y by 1 is equal to z by 3 will be some constant small k. Okay. So, you can then write z will be equal to 3k, y will be equal to k and x will be equal to 2k. Okay. So, k is the proportionality constant, and then if I have this, then I can write. So, the work done will now be integration. So, when k is equal to 0, you have these points z0, y0 and x0. When k is equal to 1, you have z3, y1 and x2, that is this point. So, I can now do the integration from k 0 to 1 and everything will be a function of k, and then you will have, just you write properly, 2 times 2k times k plus 27 k cube times 2 dk. 2 dk is nothing but the dx. Okay. Since you have this, you just do not forget dz will be 3 dk, dy will be dk and dx will be 2 dk. Okay. So, if you do, another term will be then 4k square dk plus 3 times 2k times 9k square times dz, which is 3 dk. Okay. Here what I have just done is, I have just wrote this thing, this expression in terms of k, okay, or rather this expression in terms of k. Okay. If I do this, then you do this calculation again properly, you will have integration 0 to 1, again you will have some k cube by 3 times 8, because this is 2, 2 and 2, this comes 8, and this is k square dk, which becomes k cube by 3. Okay. Then plus 54 k to the 4 by 4 plus 4 by 3 k cube plus 162 by 4 times k to the 4. And if you calculate again, you will have, you can see directly from here, you will have 8 by 3 plus 54 by 4 plus 4 by 3 plus 162 by 4. So, finally, you will have 8 plus 4 12 by 3, which is 4, and these two terms plus you will have 6 and 2 1. So, by 4, which is 5 4. Okay. So, you will have 58 units, and now if you just see, this is 58 units. So, this is not magic, that is exactly the property of a conservative force field. What I would request to you is to calculate the work done along this space curve. This is actually much more easier. You just like here I have converted everything in terms of k, there you have to convert x, y and z and all the coordinates, okay, here in terms of this t, and you have to just remark that when t is equal to 0, then you have this initial point, and when t is equal to 1, you have this final point. So, again the same type of limits of integration will be applied there, but it will be a different variable, which is t. This is a different, we call a different type of parametrization. So, that you will calculate and tell me what is the value, and you will check, you will see that this is exactly equal to 58. Now, the most important point is you do the same exercise for the other force F1, for which we did not have the work done, for which we calculated the curl and we found that the curl is not equal to 0. So, and for that what you will discover that the two amount of works, okay, along the straight line and along the curve may or may not be equal, and actually the high possibility is that they are not in general equal. Okay. And that is exactly, again nothing strange here, it is nothing but the property of a force field which is not conservative. Okay. Thank you very much.